highly efficient and stable carbon-14 dye-sensitized betavoltaic cell. I think you never heard about this research before. Yes. So as you see here, this is a very popular graph of energy consumption along with the world population. So after 1950, the energy consumption never decreased. It's always going up with population. And this is very conventional expectation. But I think the energy consumption should be even steeper than the estimation. Because we are living in the era of quantum computing. I think this technology is not fully developed yet, but sooner or later, we are going to use quantum computer instead of PC. And then artificial intelligence, we are using ChatGPT and on-device, off-device. So we use a lot of data center for using big data and Internet of Things, whatever. So I think 10 times or 20 times more data centers should be built. So as you see this energy consumption after 2024, the data center and AI consume a lot of energy than current energy consumption. That's natural. Naturally, we can think about this. Then what's the next? So it's almost impossible to avoid the energy consumption more and more, but the more we use energy, the more the global warming worse. Then the effects of the climate change on pollination is seriously bad. So one of the very famous scientists said, no more bees, honeybees, no more pollination, no more plants, no more animals, no more human beings. So if the honeybee is extinguished, then 4 years. We have 4 years. So we have to do something. But globally, smartphone emissions at the moment, 4.5 billion smartphones generate 146 million tons of carbon dioxide. And we don't recycle those things. The possibilities of disposal and recycling is very, very low. And the average age of device and trading, which means, we update or replace your or anybody's cell phone in 3.5 years. Okay. So probably most of the issue is the battery inside the device. And so while we are using the cell phones, we are burning the fossil fuels and they make the global warming seriously worse. So, but while you are using this cell phone, you never think about this issue. So the very important thing we have to realize every moment, electric vehicle or mobile phone, mobile devices are not environmentally friendly equipments. So we have to, so the study of the motivation, the study of the next generation, long-lived batteries may be different technology. So the big problem of the increasing amount of battery waste, I have never heard. I know there are some technologies and factories to recycle those waste batteries, but it's not efficient. And and it makes the environment worse. So I thought so many times, what's the next? What should we do for our environment and human beings? So I thought, why don't we put the nuclear plant inside the mobile phone, lasting 50 years battery life without charging? So I have searched the nuclear batteries. We started the nuclear batteries about 1950s. I'm focusing on beta batteries, not alpha or radioisotopic thermal electric generator. The beta battery looks quite interesting. And many people ask me safety about the beta batteries because we have to use isotope radioactive materials. But as you know, the beta particles cannot transparent to the thin aluminum foil. So if we use just thin aluminum foil to shield the radiation, that's it. The beta battery doesn't explode or fire as like lithium batteries. So it's quite safe and interesting technology. So I want to explain some the basic concept of working way of beta batteries. If there is a isotope radioactive material generate batteries, they will stimulate the p-n-type and n-type, p-type, p-n-type junction semiconductors, and they excite it and generate the electrons. Quite simple, very simple mechanism. So this is the base of basic knowledge of solar cells as well. So, but the problem is this type of betavoltaic cells already exist, very expensive for the commercialization. So I searched how to decrease the cost of making this. So this is the technology trend. So as I said, 1990s, scientists developed the betavoltaic cells for the hard phase makers and for specific extreme environmental researches. And then recently, a couple of countries are working on the betavoltaic batteries. So in my group, we have published the first paper in 2020 by using dye-sensitized mechanism, which has very low cost. So actually, I have involved in the renewable energy, such as solar cell or photoelectrode water splitting, hydrogen generation. And well, quite well-known engineers, senior scientists already have done this type of renewable energy researches for a couple of decades, but we didn't find any good answer. We may need renewable energy, but last couple of decades, renewable energy didn't replace fossil fuels. So anyway, I have studied dye-sensitized solar cell, perovskite solar cell, quantum dot solar cells, and those renewable technologies were not enough. But I know how to make them. So I applied those renewable technologies to these betavoltaic cells. So 2020, well, about 3 years, we started this research 2017, something like that, yes. Over 3 years, we have dedicated our time to develop this system. We made the quantum dots carbon-14 nanoparticles, quantum dots and nanoparticles, and applied these radioactive sources in the cathode surface. Because the radioactive power is not that high enough, so we have to add more carbon sources on the cathode. So we have to condense the amount of the carbon sources on the cathode. So when they generate the beta rays, then as I said, instead of expensive PN semiconductors, we use dye, which is just dye, okay? Very, very cheap dye, which has ruthenium metal. So this is the organic metal dye. So the beta radiation stimulate this metal organic dye, and the excited electrons flow to the conduction band of titanium dioxide. So titanium surface of the titanium dioxide nanoparticles covered by these metal organic dyes. Then the excited electrons flow to the conduction band, and they flow to the line and make a circuit, and they generate electricity. So the simple fabrication process decrease the total cost over than 30%, rather than the expensive PN junction betavoltaic cells, the conventional cells. So this is the CEM image of electrode, and this is the high resolution TM of quantum dots, C14 quantum dots, and then this is the power density of dye-sensitized betavoltaic cells, and we have tested with radiation, without radiation, with dye, without dye, and then the with dye and radiation, it shows very high performance, and we have tested several dyes, 3 dyes, with ruthenium metal and without metal, and we realized that the metal organic dye showed the better activity than normal dye. So the total efficiency is 0.48% with the short circuit current density 12.75 nanoamp per square centimeter, and open circuit voltage was 29.2 millivolts. So you noticed that the performance is very low. Of course, it is very low. It's just initiated, or the first dye-sensitized betavoltaic cells. So this is just the bottom line. We try to increase the performance from this data, and lifetime was about 10 hours. 10 hours, and we realized that the dyes were decomposed by the beta rays. So we developed the different way of technology to improve the efficiencies. So the second paper was published last year, and we tried to apply our carbon-14 radioactive source to the both electrode. So in the previous work, we applied carbon-14 quantum dots on the cathode, and then we applied another carbon source in the in between ruthenium metal organic dye and the TiO2 nanoparticles. So when we used the carbon-14 citric acid, they make a very strong bond between the metal organic dye and TiO2. So cathode carbon-14 radioactive source generates beta rays to the metal organic dye, and then this carbon-14 from the citric acid generate another beta radiation. So both directions stimulate the metal organic dye. So this type of simulation made the electron avalanche effect better than the single beta source electrode. So we have measured the performance blank cell and betavoltaic with cathode and anode, and then both cathode and anode, both radiation effect, and they showed the better performance, and the overall power density is even better than the others. And we have improved the efficiency than 2.86%. So I said the first work was 0.48. Okay, from the 0.48, we increased the performance 2.86%, and 60,000 electrons generated by the single beta particles. And the lifetime was extended to 100 hours. We have developed the technology to make the betavoltaic cells, so 10 times larger than the reported previously. And then third work. This work is just published a few days ago. So battery absorber is very important to develop the efficiency of betavoltaic cells. So we used metal-organic dye, which was not stable. So we decided to use inorganic hybrid halide perovskites, which has a high electron hole mobility, and so we apply betavoltaic beta ray absorber in between cathode and anode instead of dye or expensive PN semiconductor. And we used the additive of methyl ammonium chloride or cesium chloride additives to get homogeneous and compact structures. So without methyl ammonium chloride or cesium chloride, the particle structure is not strong enough and homogeneous. But when we use the additives, methyl ammonium chloride or methyl ammonium chloride and cesium chloride, we can facilitate the grain growth and promote the preferred orientation of the perovskite grains. So we have seen those grains by using SEM imaging, and then we have seen the C14 quantum dots on the surface of cathode, and we confirmed that. And then we have measured the properties of the electrode. So we have seen the perovskite XLD data, and then we have measured the UV visible absorption spectra, and we have calculated the band gap of perovskite, and we have seen blue shift of the perovskite when we added the additives. And we have measured the performance of perovskite betavoltaic cells. And when we added two types of additives, the perovskite betavoltaics showed the better activity. And then lifetime is now at the moment 9 hours. But we are sure we improved the lifetime of this one, because the simulation of perovskite betavoltaic cell is 28% reported. So this is conclusion. All the blacks are already reported by the other research groups. We have firstly published the dye-sensitized betavoltaic cell 2020, and we have published this the betavoltaic double-side radioactive dye-sensitized betavoltaic cell 2024, and then this year we have reported first perovskite betavoltaic, which was not that high, but we are soon submitting the new paper, the next paper. I cannot open the data yet, but the performance is very high here. So I'm pretty sure you may be excited to see this result soon as a published paper, maybe a month later. And then I'm pretty appreciate to my group members to do this research. Thank you very much.
For the amazing work. Any quick question?
I don't think we have time for that. Is Jalen here? I think we do not have time at the moment, sorry. But Jalen's gonna speak, and then there'll be time after that to ask questions, right?